So without further delay, here is your Delphi instructor, Dave Hobbs.
Hi, I'm Dave Hobbs for Delphi Product and Service Solutions, and welcome to this 1-hour live cast on gas direct injection. That's GDI. It's been around a while. We're going to give you some helpful tips, not only just a general overview about GDI, how it works, but also some failure patterns that can occur and what you can do with some of the tools you're using, whether they be basic tools or some of the advanced stuff like using a lab scope for current ramping and things like that. Let's get started with the history of GDI. Dates way back to about 1955 on a Mercedes, a mechanical system where it injected fuel directly into the cylinder. That's what GDI is really about. But it didn't get electronic until the 1996 first year for OBD2, but it never came here in the US for OBD2 truly. It was a Japanese right-hand drive car, and the Mitsubishi Galant. And then later on, we've seen Volkswagens a few years later, and also the Ford that was Europe first, and then finally in the Ecotechs came into the US along with the little GM 2.4 on those Saturn Skies. If you remember, they were the debut for GM in the GDI world. The Beamers with their V12s and so forth and so on. It is becoming very commonplace today. It's almost harder to find a new car without GDI than one with it. Now, if we look at this picture of what GDI is about, the injector, instead of being in the port, the side is going to spray in, then the intake valve opens and the fuel gets pulled in along with air. The intake manifold's just carrying air in a GDI car. That's what gives it better pumping abilities. And the fuel injector is situated somewhere in the cylinder head. And we see it here on the side with a specially shaped piston typically when they come in the side like this. And that's going to make for a lot of benefits. And we see here on this slide better fuel economy because of superior fuel atomization. We want to make the fuel as much of a vapor or mist as possible because that's what burns. Higher compression ratios are allowed due to the cooling of the cylinder and better pumping efficiency, as I mentioned before. Also lower emissions, especially on cold start. So these are some of the advantages. You're going to get also probably a 15% fuel economy gain. Now there's two different ways to spray GDI, gas direct injection. One on the left is used less often in the combustion chamber. That's called stratified. Stratified is where we have basically layered mixtures. So right in the center, we would have a stoichiometric, 14.7 to 1 or so, and out to the outer perimeter of the cylinder, we may see 20, even up to 40 to 1 lean mixtures. And on the right side of our screen, we have what's called the homogeneous. And the homogeneous is a very mixed, very well mixed together air-fuel ratio at stoic or whatever ratio we're getting ready to squirt the injectors. Now, we squirt those injectors in 5 different GDI modes. First is, of course, the homogeneous, and the second, the stratified. Then we have a double injection pulse. Also, we have a knock protection pulse. Now, the knock protection is typically sprayed after top dead center so that we can add a little fuel into the cylinder if the ECM detects knock. And what that's going to do, instead of retarding the spark timing, which is going to kill power, we're going to make the cylinder mixture a little richer, and that might not be as great for emissions, but when the NOx comes down, the overall benefit is definitely noticeable. So we get rid of NOx by spraying a little extra fuel to cool that cylinder down. And then finally, stratified catalytic converter mode is where we're going to spray extra pulses that we really don't need on cold starts that's going to help with the extra fuel in the catalytic converter to get it in the light off mode quicker. And as you well know, the faster we get the converter lit off, the lower the emissions are for those cold starts. Now let's get started with the hardware of how these systems are laid out. Like any system for fuel, you've got to have a source of fuel and you've got to have a way to get it up to the engine, and that's not changed hardly at all as far as the hardware goes. We've got a low pressure tank, in-tank modular fuel pump assembly, and that's going to spray that fuel or push pump that fuel up to the fuel pump. We also have a low pressure sensor mounted somewhere on the low side of the system. Now from that pump you see in the middle being driven off of a special lobe on the camshaft, you're going to have from the pump down, what's the low side, and from the pump up, it's called the high pressure side. So just like in air conditioning, you have a low side and a high side, or in diesel common rail systems, we've got a low pressure side and a high pressure side, much the same. So down there in the tank, we've got the float unit, we've got the pump, the strainer, maybe a filter in there as well, and of course the fuel vapor pressure sensor if the vehicle uses that kind of evap system. So very familiar looking pumps are in that tank, and what controls them though, not just a relay, a little bit different unless you've worked on Ford SFIs in the past. Okay, now here's that pump. Again, not a big radical looking change of difference between a sequential SFI vehicle that you're used to and GDI. But what is different are these fuel pump modules. Now, if you've worked on Fords, as I mentioned, with sequential fuel injection in the last few years, you've seen these modules starting to pop up. Key turns on, computer, ECM, PCM talks to that fuel pump control module, and it gives some kind of a duty cycled power pulse to the pump in the tank. Same thing going on with GDI. As a matter of fact, all the GDI vehicles I know of have a fuel pump control module controlled by the PCM or ECM. So we're going to pulse this pump with a particular frequency. We're going to actually see it hands-on the vehicle coming up in this broadcast. All right, now moving on to the hardware, the high pressure side begins with the fuel pump, the high pressure mechanical fuel pump driven off of a special lobe on the back of typically a camshaft, and of course the high pressure rail. So here we have the rail, we have the high pressure rail sensor. If you do diesels, you basically have GDI nailed as far as the general operation, only at lower pressure. Still much higher than sequential, but definitely lower than the 20 and 30,000 PSI that we see with a common rail diesel injection. But it is high at several thousand PSI. In fact, we've got rails with special seals and so forth, and they have sometimes special tools required to pull them into the head to get them seated. Here you see a V8 engine with that rail pretty much buried. So here's the deal on diagnostics. Going to be hard to get a Noid light in there and check injector connectors. You're going to be doing your injector testing elsewhere, not at the rail. Typically, especially in a V-configurated engine, those injectors are super buried, and also you will see around the pump and sometimes the injector for sound and temperature insulation, some material like this, important to put it back. Just like that stuff hanging underneath the car that's designed to channel air so we get good breathing, you don't want to leave things like that out. In fact, oftentimes it's going to crumble when you take it out to access a part. Make sure you can get a new one and put it back in. It belongs there. Now, there's the fuel rail pressure sensor, a pit on the scan tool you can look at, and if you can't, you can always back probe it and compare the voltage you get. It's just like a map sensor, the voltage, analog voltage you get to a chart in the service manual will tell you what that pressure is, and it's going to be somewhere between 500 and 2,800 PSI on average, depends on the model and the OEM manufacturer. The direct injectors are pushed down with a special Teflon seal into the cylinder heads directly. And there's what they look like as far as the electrical connection. On the left, two types here. Solenoid type, that's what we're used to. Most gasoline engines and even most diesel engines, with the exception of some 2010 and newer stuff, have a solenoid-based fuel injector. On the right, in the middle of your screen right there, that's called the Piezo-Electric Injector. And what that is, it is the reversal of a propane gas grill starter. You've all used those where you pushed a button against spring tension and it finally got to a certain point and you hear a click. And that click was a bunch of those piezo wafers being mechanically moved, and that causes a voltage to be provided or produced. In piezo injectors, we do the opposite. We take a bunch of voltage and we apply it to those piezo wafers, and that causes them to expand just a bit. It's a very minor amount of movement, but it's just enough and it's powerful enough that we can then open a valve and let the fuel flow out the bottom of the injector. So we're going to see more of these, and they are going to be very fast, and they're going to be a little longer than the typical solenoid-based GDI injector. So look for that on some of the Euro cars that's out there already, I believe. There are some advantages of piezo on top. You can see from left to right the the procession of as fuel starts to spray, how big it gets, how well defined the spray pattern is, much superior with the piezo compared to the solenoids. So we'll be doing most of our diagnostics today on the solenoid system, but I did want to mention the new piezos as they come out. Also, here's cutaway of injector, typical injectors here on the left, and then there is a blow-up of an injector. You see just a basic Viton type rubber O-ring on the top that goes in the rail, but at the bottom we have that Teflon seal. We'll talk about replacing those here coming up. Now, continuing the high pressure side here, there's the pump itself, and I've got one here on the table. This is going to be mechanically driven by a lobe with several, actually I should say a back of the camshaft, which could have several lobes, 2, 3, 4, whatever the manufacturer is using. And there'll be some kind of a follower, you might call it like a lifter or cam follower between here and that lobe. Some are roller type bearings, others are flat tappet type. Depending on the type you've got in the vehicle, a lot of the Euro cars I believe use the flat tappet type, is a big issue when you don't use the right oil. If you're not using an ACEA European spec for that particular vehicle, it's still 530, but you're using the GF5, the Ilsac Dexos on the Euro car, or vice versa, the Euro oil on the American car. A typical complaint is the same thing you get if you don't change the oil often enough, period, no matter what kind of oil you put in it, and that's premature pump failure. When these guys fail, they oftentimes will have the pattern failure characteristic of just getting super noisy and losing some pressure. Now we'll talk about later how some of that pressure is compensated for with the low pressure side of the system. But for now, just remember, if you hear a knocking noise on a GDI equipped car, now they all make a little bit of noise, like a little bit of lifter noise. Sometimes you can hear those injectors and hear the pump. But when this guy starts knocking, you'll swear it's bottom end rod or bearing noise of the crankshaft, and oftentimes it's this dude. I've seen a lot of these in the GM warranty parts bins and so forth. They've had issues, the customer's not changing their oil properly. So make sure you look into that next time you have an engine noise. Could be one of these. Now what makes it tick is the solenoid on the side of it. So here you see in the photo on the screen, you also see live in my hands a 2-wire connector. This is what the computer controls to dictate how much high pressure this puts out. Obviously the speed of the camshaft is going to have an effect on how much it pumps, but how much we actually apply to the rail is dependent upon the solenoid, the pressure control solenoid. You also see on that particular one on the screen, and not here in the one I have on the table, you'll see a Schrader valve. That Schrader valve is for the low pressure side of the system. Now let me give you a little caution here. Do not, I repeat, do not ever try to jury rig a low pressure common sequential fuel injection fuel pump pressure gauge into the high side of any GDI system. Not only will you ruin your tool, lose the money from that, you also might lose something else, maybe an eye or something, as the gauge basically expands a little faster than it should. In other words, it's going to explode into pieces. So do not ever use a low pressure fuel gauge on a high pressure system. Use the fuel rails pressure sensor PID with your scanner or back probing the meter, and that will be what you need to check low pressure, high pressure. But low pressure on some of the earlier GDIs with GM did have the Schrader valve. You can put your good old-fashioned fuel pressure gauge on there or your transducer if you're using that to scope, and you'll see the low pressure system, 40, 50, 60 PSI, whatever that system is on the vehicle you're working on. Speaking of using the pressure transducer, if you do indeed hook a pressure transducer to that Schrader valve to look at the low pressure side of the system, keep in mind every time that solenoid turns off and on, we're going to have some backfeed of the high pressure into the low pressure system, and that will make your signal a little erratic, and that's what you're seeing basically, a telltale that solenoid doing some backfeeding. 870 to 3,000 PSI on this particular model we see right here, single piston design. Let's see what the solenoid's really doing in this illustration. On the left, we see that the solenoid has been turned off, and we are allowing, I should say turned on, we are allowing the pressure to backfeed as that cam turns around to the center illustration. Some of that pressure, that cam came up and made that pump pressurize up is going back to where the low pressure source came from, the fuel tank. But if we close the solenoid, that's when it turns on, I should say. We turn the solenoid on, we pull it up. Now we're going to block the flow of that high pressure created in the pump from feeding back to the tank, and now it's all going to be pressurized and go to the rail. So if I don't want it all going to the rail, I'll turn the solenoid on less. If I want it all going back, actually back to the tank, that's when I turn the solenoid on less. Turn the solenoid on more, that's when pressure goes up. So duty cycle goes up, pressure goes up. Duty cycle goes down, or you unplug it, pressure goes way down, almost to low side pressure, basically. Now, let's take a look at where these things are in the vehicle. Here is a Kia Optum, it looks like, 4-cylinder, and there's the pump right on the top back of that 4-cylinder twin cam engine. There's a little blow up of it. You see the low pressure snap-on to quick disconnect fuel line, and right there in the front and over towards the right-hand corner, you see the high pressure line, and you see the solenoid connection. Now, a little note on the high pressure line. This is what you don't want to do. You do not want to take it loose if there's pressure on the system. Because when you crack it loose with a wrench, you could, if the system's still pressurized, and we'll talk about how long it can stay pressurized and how to power the pressure or depressurize it in a minute. But for right now, if you crack that loose, a really fine stream of gasoline could come shooting out of there like a cutting tip on a pressure washer. And you know what that can do? That can poke a hole in you and give you blood poisoning from that gasoline in your bloodstream. So never crack it loose, but when the system has been depressurized and you've confirmed that, and you do take the line loose, get a new line, because you can't reuse them. It's a ball type of a fitting, like a lot of the diesel injection stuff, and you know some of them can be reused, the little transfer tubes between the rail and each injector, and some can't. So in this case, most of them can't be reused because they'll make a particular wear spot as you tighten that up, and then when you put it back together, it might not be the exact same spot, and therefore the wear spot's at a different point, and you get a slight leak. So the pipes aren't that expensive. Don't reuse them. Don't re-torque if you think it's loose. Get a new pipe and torque to specs. Now, here's that caution coming up with any GDI class. The pressure can remain there for a couple hours up to that point, and this can be very hazardous. So wear eye protection, keep your skin covered with sleeves and so forth, and always use the appropriate manufacturer specified service procedure in order to stay safe. Now, here's some points I'll make here just on my own. GDI systems I mentioned can be pressurized for up to 2 hours. Follow the shop safety procedures, make sure you have a fire extinguisher handy, and wear personal protection such as your goggles, and you should be fine if you do one of these two procedures prior to opening up a high pressure GDI system. Now you can still work on the tank and so forth on the low pressure side and depressure it in the normal manner you've always done with sequential fuel injection systems. But on these high sides, do one of these two procedures. Procedure A is simply wait 2 hours, and then just on the safe side, you go ahead and you crack this loose with some shop towels around it just to catch any kind of a dribbling fuel. Procedure B, if you don't have the patience to wait 2 hours, you got to get on the job, get it done, then go ahead and crank the engine with either the fuel pump fuse, that's the low pressure pump in the tank, or a relay removed, or take a bidirectional scan tool that can turn the relay off, turn the pump off, actually command the fuel pump control module to turn the low pressure pump off. And when the pump's off or the fuse or relay is pulled, the vehicle, basically you run the engine until it runs out of fuel, and then you double check with your scan tool for the fuel high pressure rail PID pressure. So you're looking to see if it goes from, let's say, 800 down to 0. When that pressure's at 0, you're safe to crack the lines loose and not have an issue. Now, I'm going to add one more step into that. That's my personal preference. And this is what I do. I take the battery cable off. And I know that's a pain, relearns and so forth, but here's the reason why. Some manufacturers are experiencing vapor lock. Now, vapor lock, I thought, was an age-old problem that went away ages ago. Apparently not. I had a 2010 model GDI vehicle. It had every symptom after a hot soak of vapor lock. If you're young tech, to remind you what vapor lock is, it is where fuel boils in either a fuel line or a fuel rail. And now when you go to restart the engine, usually after a hot soak, this happens, you go to restart that engine, that gas now can't get past, the liquid can't get past the air bubble, and you have a lean or a stalling or no start condition. So high pressure systems came on board, not really that high, TBI, 9 to 12, PFI, 35 to 45 PSI, and we never heard of vapor lock again, really, for the most part, until GDI. Some GDI vehicles, the fuel will boil in the rail. It's been confirmed by some of the OEs, and one of the solutions by one OE at least was to do a reprogramming of the computer. And what the computer did, the ECM, it would wait for a while, seen a hot engine, and it would, with the key off, just like it does evap with key off, it would turn the electric pump on in the tank. And that would just run for a couple of seconds. And you would also hear, when you heard, you're sitting in the car and you're hearing that's about 10 minutes or so after you turn the key off. You also hear, beside the pump and the tank running, you hear some clicking under the hood. That's the solenoid here. What we're doing is we're allowing the low pressure fuel side to go right past the solenoid in the high pressure pump, right into the rail, and we're pressurizing that rail during a hot soak to get those bubbles of air out so we don't have the hot soak restart, stall, hesitation, and rough engine associated with vapor lock. So because the pump can run with the key off, would it make sense if you don't want 40, 50 PSI of low pressure squirting all over your job site where you've got some lines loose at the engine or back of the tank or whatever, wouldn't it make sense to make sure that pump can't be turned on with that key off, take the battery cable off? So that's what I like to do. Now, in this little illustration, this schematic from a typical late model Ford Ecotec, we have the fuel pump control module that every GDI vehicle, as far as I know, has control the fuel pump. Now, Ford, instead of using, this is a brand new Ford Escape actually, and instead of using a CAN bus to connect between the PCM and the fuel pump control module to tell it what to do, we have a couple of circuits called FPM and FPC, fuel pump monitor, fuel pump control. Now, fuel pump control is really what you're after to see what's going on. Let's say you have a no start and you have no low fuel pressure. What's happening? You don't hear the pump in the tank running. You could back probe that with a meter or scope, and you should see a square wave. You'll see a pulsing signal, a duty cycle that changes, a frequency that's fixed, and it's fairly high frequency, and that's going to be telling that electronic fuel pump control module how fast to run the fuel pump itself. Now you'll notice FPM is a wire also between the module and the ECM. What that's job is to do is to tell that ECM how the pump's doing. And I've looked at this signal on a scope, and it's very sporadic. It's just basically every couple of seconds you'll see a little square wave. Really can't see if it's got a problem or not, just that it's there. That's all you're looking for. But now the output of the pump, or I should say the output of the pump control module to the pump, you'll notice we have the symbol like this for twisted pair, and we also have the little symbol of dotted lines for a shield, a braided shield. So definitely an EMI issue. Why would there be an EMI issue of wires simply giving power and ground to a fuel pump? Because they are pulsed 10, 15, 12, whatever kilohertz. These are pulsed very fast, a fixed frequency once again, and a variable duty cycle to run the pump at different speeds with different duty cycles. So again, a meter with a frequency counter and duty cycle function, or a scope is what you would need to really look at the voltage supply from the fuel pump control module to the pump itself. Now here's the GM version here, and we're using a CAN bus message between the PCM and the fuel pump control module to tell it what to do with the pump. Now, to look at this a little bit further, we're going to actually go to the vehicle and do some scoping. Now, anytime you want to do any scoping, you definitely need a pinout to tell where the powers and grounds are and to look at the signals in, the signals out, which we'll do. And also, you need to kind of know what to expect with the gas direct injection pump as far as the current draw. So if you've got yourself an amp clamp and you want to see what the current draw is, say you're advanced tech, and you know there's more to a fuel pump operation than just voltage. Now, voltage is important. When the system is powered up, the pump is running or trying to run, back probing between the pump supply voltage and B+, maybe up at the battery, tells us voltage drop of the wiring between the front of the vehicle and the pump itself. Really common to have voltage drops cause a loss of fuel pressure. In addition to, you'll see low current draw of the pump, and the pump's just not going to make enough pressure or any pressure at all. But in the cases of sometimes it's not voltage related, it's simply current related. That's why we have this chart here. So between 4 and 6 psi on a sequential fuel injected engine, if it's central port, it's a little higher pressure system, it's between 7 and 9. So the more pressure the pump makes, the higher the current. Now, what is a GDI, in-tank low pressure pump, going to draw? We'll find out on the vehicle. But also what we want to look at is if you're really into the advanced side of diagnostics and you do current ramping, you'll recognize this right here. This is an old 99 Chrysler Sebring with a basic in-tank SFI pump, going to make 40, 50 psi, whatever. That guy is bad. You can tell it does not have the very rhythmic plowed field of the signature of the armature turning from armature spot to armature spot, bar to bar, commutator bar to commutator bar as the brushes move. You normally on a good pump see a nice rhythmic signal like that. We'll see in the next slide. When you put your amp clamp on top over the wire feeding the pump and you connect it into your lab scope, we need to see something like we're going to see in the next page. But we notice the voltage is hanging in there. You can't see the voltage scale on the right, but I'll tell you, it's about 14.5 volts. That's a good rock solid, no voltage drop going on there. We don't have any bad connections, but we do have a bad pump, and it's only running about 3 amps. You look at our scale here, 6,000 milliamp scale, about 3,000 milliamps, so 3,000 milliamps, 3 amps, and that's a little low for an SFI vehicle. Now we see a good signal. That's the pattern you're looking for, whether it be a GDI pump, and I'll give you a little disclaimer when we go to the car, or a SFI pump. You'll see the plowed field of the current changing normally as the armature turns. And there's my voltage up nice and high. Now, but look at the actual amount of current. Here we have about a 4,000 milliamp scale at the top, and I'm only drawing about, that should actually have another zero on there, 1,500 milliamps or 1.5 amps. So 1.5 amps is not near enough for a pump to be drawing, but it has a good pattern. So what's wrong? I got good voltage, low current, and a good pattern. Not enough fuel going through the pump. A clogged strainer can do that. So you have a great pump, great voltage supply, low current, low fuel pressure. Strainer is keeping fuel from getting into that pump thoroughly. The pump will burn up eventually after it just has too much heat and not enough fuel to cool it. Now on the other side, if you have too much pressure, good voltage, too much current, low pressure, good voltage, but too much current, that would be a pump that has a struggle getting the fuel through it. So it's pulling plenty through it, it's drawing lots of current, and it's trying to now jam it into, let's say, a clogged fuel filter, and you'll have high current, good voltage, high current, low pressure. So these are things to review before we go in to apply these principles to GDI. So there's a good pump now. It's got plenty of fuel supply, and it's not got a restriction on the other side going forward. Good voltage, we've got about what? Good pump, 20 amp scale now, 7 amp draw, that's what we're needing to see. Now, let's go to the vehicle and talk about GDI low pressure pumps with amp clamps, meters, scopes, you name it, get you ready for some hands-on. When we started the car up, we're going to take a look at what's going on with a meter first and then the pico scope. Now, what I'm hooked into with the meter is the power supply from the fuel pump module down into the in-tank modular fuel pump assembly. Very much, as I mentioned before, a similar pump, what you're used to dealing with. But now we've got a fuel pump module, not a new thing. If you're a Ford tech and you've been working on some of those sequential injected Fords, they're doing a pulse width modulated output from the module down to the pump as well. But this is very fast. If we just look at the raw voltage averaged out on the multimeter, I've got about 5 volts, meaning we don't have a voltage drop. We have a duty cycle that's off and on. Let me turn the meter to duty cycle. And we're on about 38 or 39% of the time and off the remainder. So that's why I only have about 5 volts. That's normal. If you didn't know that, you'd be replacing a fuel pump that was okay, or a fuel pump module that was okay. So we'll go ahead and go to hertz now. 24.99, we'll call it 25, and look at the K for kilo Hz, hertz. So 25,000 times per second, this is turning off and on. Let me adjust the time based on my scope here in a second. But that's giving you an idea of what you can see with your meter. If you've got a meter that can measure frequency and duty cycle, you're in pretty good standing checking these fuel pump modules out and to see what is going out to the pump from the module. Obviously, the duty cycle will fatten up if the pump under the hood is struggling to make the necessary high pressure that we need for those direct injectors to deliver the correct amount of fuel. Let's look at our scope now. There we go, there's a square wave. So we are duty cycling. That's the same thing we saw on the meter. There's our 25 kilohertz and about 38 or 9% of the time it's on. Pulse width modulation, duty cycle about 39%. The red line I'm hooked into, that's the voltage from the pressure sensor. So just like there's a pressure sensor on the rail for high pressure, there's a pressure sensor typically near the back of the vehicle, near the pump for the low pressure. So if you were not able to read that particular pit on your scan tool, you can always back probe like we're doing here. Actually, you can't back probe a connector on this module that's the latching style, so we did have to pierce the wires with our probes, but then we'll cover those little holes up later with some clear fingernail polish so we don't have some of the corrosion and so forth that could get in this trunk, knocking that wire out, making that wire break later down the road. But we are probing the wire and we're seeing about 2 volts, which would equate to some amount of pressure, which we'll see later as we read the PID on fuel pressure. Or we could break into the low pressure line up front before it gets to the pump with a universal pressure test gauge. Some of them had Schrader valves on them, so that's pretty good news if you're working on a GM vehicle. But in 14 or 15, they did away with the Schrader valve, so now you got to break into the system. But why break in when you've got a sensor already at the pump? We can measure with a voltmeter or a scan tool. Now, just like any other car with an electric fuel pump, we can do the current ramping where we take the amp clamp, as we've discussed, put it around the power lead going to the pump. But we need to see what it looks like now if we're pulsing this thing at 25 kilohertz. Is it going to be a different looking signature for our current ramping waveform, or is it going to be the same? Let's take a peek. So now I've got my amp clamp set. I've got the milliseconds per division at 10 milliseconds per division, and we're seeing the familiar looking, very rhythmic plowed field, very consistent. No inconsistencies jumping in, indicating a bad spot on the armature, something electrically wrong with the pump. This pump looks good. Now, let me give a little disclaimer here. Some GDI cars, due to the nature and speed, the frequency and so forth of the fuel pump module, can make it very difficult to do current ramping waveform analysis. So get used to checking known good vehicles to see what you can and can't do. This vehicle performed very well for us. Now, if we saw something crazy jumping into this pattern rhythmically, that's going to indicate a pump that it's on its way out. If it runs now, I can guarantee you it probably won't continue to run very long. Remember, your amp clamp and current ramping is your CAT scan and MRI into the life of the fuel pump. Very easy to do if you got a lab scope and a couple minutes and an amp clamp. Well, those solid-state components they call injector drivers in the ECM PCM that control the injectors are a little bit different than what you're used to with sequential fuel injection. We're going to control both the high and low side for voltage and current. And the driver is going to provide up to between 55 and 65 volts to the injector. Now, where does it get this voltage? The same place the computers get the voltage to fire diesel injectors at such high voltages, and that's from the capacitance effect of when we turn the injector on initially. Doesn't have quite enough oomph to do the job, but we get a voltage spike, a flyback voltage from the inductor collapsing. That goes into that capacitor in the ECM, and the injector drivers use this capacitor then to discharge back out under the hood and give you the higher voltage to those injectors. We'll see about 10 amps of turn on initially, the current for the injector to do its job, to turn on and point up against that high pressure in that common rail, about 10 amps to ramp up, and then it's going to maintain 3 or 4 amps for the remainder of the injection event, or I should say events, because there may be more than one pulse within one event. And that's going to only be about the 10 amp for about a few 100 milliseconds, and then we do a longer period of time with the lower current. Same thing for the voltage. So we see 65 volts or so for a brief period, and then we see about 13.5 volts or so for the remainder of the event. Now, the replacement of injectors, should you need to do this, there'll be hold downs that sometimes can be deformed, so you may want to replace those. The O-ring on top of the injector, and a secondary or a backup seal, sometimes called a plastic washer, that may need to be replaced, and also the Teflon seal at the bottom of the injector that goes actually into the cylinder head. There's a special tool, typically to get the old one off, slide the new one on. Consult your service manual to see what parts need replaced for sure and the procedure on doing it the right way. But it's not like pulling the old ones out, putting a little lube on the O-ring and sticking it back in. A little bit more work to that, but it's doable in the shop. Now, speaking of doable, let's go back to the shop and look at that Impala that has direct injection. We'll look under the hood, and we'll hook up our lab scope and our meter and see what we can find. If you're a high-end tech doing diagnostics and you want to go beyond the P0300 series codes for misfire, you want to find out more about why the cylinder is misfiring, obviously one of the first things you're going to check, is easy to get at, is the connector for the GDI injectors is going to allow you to back probe and get good old-fashioned resistance. And we see here on number 2 injector, I've got about 2.8 ohms. Pretty normal, known good vehicle. Can't emphasize that enough. Getting used to known good vehicles before you look at problem vehicles. Obviously, it's going to change a little bit with temperature as it fluctuates between 2.8, 2.9 or so ohms. Check the spec on your vehicle and see if the injector winding is shorted or open, and that'll give you a clue of what's going on electrically with that injector. But beyond that, we can back probe it and look at voltage and also use the amp clamp. If you're an advanced tech using a scope, you can use that amp clamp to look at the current ramping of the fuel injector. Now, the fuel injector's got a power feed and a control circuit. Both are being monitored and controlled by the PCM. So let's go ahead and fire this engine up and look at injector number 2 with some scrutiny on this picoscope. So we've got a pretty fast time base, so we can really see the pattern stretched out. So we have to be quick and catch it. I'm going to raise the engine RPMs a bit. All right, you can slow down. I did a DSO, digital storage oscilloscope capture, and we'll scroll back through and we see the injector voltage is 65 or more volts, pretty close to that mark. Where does it get the voltage? Just like the diesel injectors do, where we make that inductive spike when we try to fire the injector, and that flyback voltage, that spike that happens when you turn an inductor off, you shut the engine off, is then absorbed into a capacitors in the PCM, and then that goes back out with the higher voltage then to actually make that high pressure, high voltage injector have the high voltage applied to it. Now, in addition to that, we're seeing the current draw of the injector. You see it start ramping up when the injector first turned on, is when we started seeing the current ramp up, and you see 2 quick little spikes. You will see those spikes change in the number of them and the distance between them as the engine speeds up. We're not just giving it one spray, we're giving it a couple of buildups until we have the longer spray as you see towards the right. So we've got a couple of blips within the injector winding pattern here, and then it finally turns off, and we see how that pintle bump turns on right there in the middle of the injector current buildup and then ramps back down. So get used to how these look a little different, but some similarities where you can do diagnostics as you've always done with your meter and your scope on the GDI injectors. Well, we were just on a pretty late model. I mean, you can't get more late model than a 2015 Chevy Impala. Here's a 2012 Impala, had the 3.6 GDI. Tech 2 would still work on that vehicle. And here's some information I got off of my Tech 2. We've got 38 PSI on the low side from that in-tank pump, and we've got 9 megapascals. Now, there's a way to multiply that, but you could do the division and see the relationship to get you PSI. So we're actually giving you the best of both worlds with the Tech 2, giving you voltage actually, PSI and megapascals. But about 1250 if you like PSI on the pressure, the rail, and 38 coming in. So we got 38 coming in and 1250 going out. What controls that? Well, two things: the speed of the pump via the duty cycle from the fuel pump module to the pump, as well as the solenoid, the little spill valve right here that's going to allow some of that high pressure that this pump makes back, and the rest goes to the rail. So as we change conditions, the engine speeds up. We go through some different periods where I did some captures of data, 42 PSI and about the same amount of pressure there at the rail. But then when we really get into it and we need more fuel, 2400 PSI, that's getting close to the top, and 58 PSI. So two of these working together, we are doing more turn on of the solenoid, allowing more of that pressure to be blocked from here and has to go here to the rail, and also more pressure coming in to begin with. And those two things helped you get more fuel into the engine, along with the injector on time and the number of pulses. Now, things that can go wrong in diagnostics. Well, I bugged a little Kia with the Delphi GDI system, and I got this code, and I bugged it by simply unplugging the fuel pump control solenoid. When I unplugged it, I would have thought I would have got the DTC for the solenoid. I didn't get it initially. I got it later. What I did get was immediately, actually on the second ignition cycle, which is any OBD2 you expect, I got this P0087 fuel rail system pressure too low. Now here's what happens when this goes on. When this guy's not putting out enough because it's bad mechanically and it's not doing the job, or the solenoid has been disconnected or is not working correctly, you'll get low pressure. That's what the code says. And that pressure was about 86 PSI. And the symptom was it idled good, nice, steady, round town driving, but when I stomped on it, I had no power. I swore I had a clogged catalytic converter, but it wasn't. It was low, high fuel pressure, low pressure on the high side. And so there's something to keep in consideration when you're driving these cars. A little different symptoms, or the same symptoms we're used to, different things can cause those symptoms compared to what we've had in the past. Now looking more scan tool data, here we have the top PID fuel rail pressure. We see we got 600, maybe down to even like 50 or 100. So we're kind of toggling around low pressure there. The fuel pump itself in blue, and that's the percentage of on time to that fuel pump in the tank, and it's hovering around 25 or so. It dips down to about 20, and you'll see the fuel pump control or fuel pump monitor. This is a Ford EcoBoost, so it's using a duty cycle from the pump to the tank, or the pump module to the tank, but then the signal from the pump module back to the PCM saying, hey, I think the pump's okay or it's not okay. There's those little sporadic pulses I was talking about earlier. And then, of course, at the very bottom, we've got our fuel volume control valve. So the duty cycle, what's going on here. Now, as we progress and stomp on this accelerator of this little Ford Escape with the EcoBoost, we're seeing we ramp up that fuel pressure. At the same time, we're ramping up the solenoid on time. So solenoid on time goes up, high pressure at the rail goes up, and look what they're doing to the pump pulse width modulation as well. To help with all this, we're making that pump in the tank turn faster by a higher duty cycle, turning it on, and you see the sporadic little pulses of the fuel pump module saying, hey, I think the fuel pump's okay. All right? And as we go ahead and slow down off of that wide open throttle, we see about the same kind of relationships. These are the things we want to look at, again, on known good vehicles, as we can get our feet wet and learn our way around GDI systems by looking at scan data. And as we finally finalize out, we see a couple of blips at the end of the throttle. Everything is pretty much going hand in hand relationally. Now, some things that can go wrong with GDI is fuel. Obviously, flex fuel vehicles can use ethanol. Those that aren't flex fuel cannot, for the same reasons of any conventional non-GDI system. But top tier fuel is definitely being recognized and advised by a lot of OEs who are seeing carbon deposits. Some OEMs say it's an issue with oil. Some OEMs are saying it's an issue with fuel. A little bit mixed on what causes it, and quite frankly, I think it's a combination of everything. But top tier fuel, Google that yourself to see in your area which fuels from which suppliers are what the OEMs call the top tier, that have the right amount of detergents and other things that your vehicle needs. Basically the food for your customer's car. Make sure you advise your customer on the food to feed it. Now, just as a little FYI, detergents in today's top tier fuels and also the sub top tier fuels have been reduced by 50% in recent years. The reason is emission standards have been strengthened, and now some of those detergents, they're deeming that, we thought it was good for upper intake, for injectors to keep clean and so forth, even valves and so forth. Now the EPA is saying you got to take some of that out. It's causing some pollution, some air pollution. So there's why we're having some other issues in recent years that we haven't had before. Fuel keeps changing. Now, what can cause these deposits besides fuel? Well, obviously the big source is dirty crankcase vapors. Some engines are just dirtier than others when it comes to vapors. Some are cleaner. Obviously, the more your customer stays on top of preventive maintenance with oil changes. Not following the oil life monitor like a zombie, but following it with some of your good advice, as well as using the correct oil, like we talked about earlier for lubrication, also for vapors. The PCV system can work more adequately, even though we are going to get, because of the nature of how PCV works, we're going to get some buildup in that upper intake, and that's going to get on those valves as well. In addition to PCV, we have the EGR. Either it's EGR itself, or if you have variable valve timing that does the job of EGR, there's going to be some exhaust carbon deposits possibly accumulate on the valves. And a lot of the OEMs are saying the injector timing, injector position, in addition, of course, to top tier fuel or lack thereof, is an issue for fuel deposits. We've noticed that some of the late adopters of GDI, some of the OEMs that got it later than the others that went in really early 10 years ago, the later adopters have timed the injector, positioned the injector, and basically have less issues with carbon deposits than some of the earlier ones. Now the question is, what do you do with it, and how do you inspect your customer's vehicle for the carbon deposits we're talking about? Let's go to the car and take this little handy USB inspection scope and show you how you can sell intake valve cleaning to customers with pictures, because they're worth 1,000 words. Carbon deposits on the back of intake valves for GDI vehicles are problematic, especially with the European vehicles and some of the Asian vehicles. So what's one way to determine if you've got the valve deposits? Well, ideally, it'd be nice if you could pull the spark plugs out and take the mirror lens on some of these bore scopes and look around in there. Most of them are not going to have enough powerful of a light to let you see the valves. So an upper intake manifold plenum removal is in order. Now on this V6, I had this thing off in just a couple of minutes, so it's not a big deal. Now we can easily see the valves if we kind of maneuver ourselves in a flashlight, but if you want evidence to show your customer, a scope like this is very, very handy. This is a USB type of camera. These are becoming more and more popular these days, around $100 or so. And you can see the image we're looking at right now is the back of a radiator. So radiator condensers, hidden bolts, all sorts of other things that are hard to see and yet let alone hard to tell your customer, show your customer what you've got. This scope is going to be well worth the money. So I'm going to take a look at, well, as you can see in these back cylinders, we've got some carbon deposits already, even though we only have 7,800 miles on this new Chevy Impala rental vehicle. And if I move over to another set of cylinders, pretty much the same thing. So we're seeing the start of formations. What could be done is this could be tracked. You could take a screen capture, print screen or snippet or one of those kind of programs, and turn this into a file, keep permanently with your customer so that we can track and see how bad the carbon is building up. Or if it's a higher mileage vehicle and you get to this point for inspection, as they always say, a picture is worth 1,000 words. Video is even better. You could actually record the video with some of the freeware out there to record video. So again, very handy tool with a very common problem on GDI. Well, there's a way to do the inspection and a vehicle that's just starting to build some carbon deposits on the intake valves. Here's an illustration of what they can look like when they start to get worse, and it can happen fairly quickly. The deposits are described as sticky coating of oil and fuel elements that serve as a little base for more carbon to stick to more and more. So it's kind of like an ice cream cone. Things just start sticking to it. And there are measures out there to combat this after it builds up. It's inevitable some will build up, and a little bit is not going to be an issue, but when it starts causing drivability issues, stalling, hesitations, misfires, there's where we need to get a little bit more drastic with it, like in these photos here of a cleaning solution being applied into the port with the upper intake removed like we did on the Impala, and the valves are of course closed. You let that solution sit and soak and do its job, and then you use the little brush to tighten a little bit of extra work to get the valves cleaner. But make sure you evacuate as much as you can from what you just removed, because where's those deposits going to go? They're going to go into that engine, then be burnt right out the exhaust valve and into the catalytic converter, which is not going to do it any good. It's definitely going to possibly do it some harm. Now, another method that's been out there and actually been resurrected from the early 90s when we had intake valve deposits due to other reasons on sequential and port fuel injected cars, and that's the walnut shell media. It's kind of like sand, but it's made of walnut shells that is blasted with shop air at the back of the intake valves. So instead of putting it in through the injector port like they did in the early 90s, and BMW and other manufacturers came out with this carbon blaster tool that was accompanied by a shop vac, your shop vac, attached to, as you see on the right, an adapter that would fasten, in the case of the GDI vehicles, because we don't have a port injector to pull out that gets at the back of the valve. Now we're going with the intake off and we're going through the port, and we're actually blasting with that little adapter the shop air. You see the gloved hand there, those little beads, the fine ground up walnut shells at the valves and the shop vac, pulling it out as fast as you can blast it out. Make sure you get those little pieces of carbon out. Again, it's not going to do the catalytic converter any good, that's for sure. Now, let's go to some quick little questions for you, and then we'll go to questions from the field. Number one I've got for you is this. Most GDI systems typically have low side fuel pressures of A, 20 to 30 psi, B, 30 to 40, C, 50 to 60 psi, or D, 70 to 80 psi. Make your choice now. We'll see how much you remember. Catalytic converter to light off is accomplished through which of the following? The injector is pulsed multiple times. A, it's impossible to bring the converter up to temperature on a cold start. B, or C, a special O2 heated sensor circuits. Which do you think is the correct answer to getting the cat lid off at cold starts? The answer to answer number 2, if you've seen that, was A. All right, number 3, on high pressure pump connections, care should be taken to A, use the correct dielectric lubricant on the threads, B, taking into consideration the use of left-hand threads, or C, not reuse or retorque high pressure lines. Which do you think is the correct answer? What do you remember? All right, well, it looks like 66% of you were watching got the answer right. You nailed it. C, don't reuse these high torque or these high pressure lines. Don't retorque them. Put new ones on. Number 4, most GDI systems, the PCM sends how many volts to the injector? A, 14, B, 65, or C, 120. Make your selection now. Well, 100% were correct, 65 volts. Way to take notes. Let's do the last question now, and then we'll open it up to questions from the field. Number 5, before disconnecting lines in the high pressure system, you should do which of the following? Command the low pressure pump off, A. B, remove the fuel pump relay, or C, none of the above, or D, either A or B. All right, over 80% of you were saying answer is D as in Delphi, either A or B. You could take the pump relay out or you could command it off with the scanner, run that thing out of fuel, check, make sure that that PID for the high pressure rail is at 0, then you can start cracking lines loose and not have any worries. Now, let's open it up to the field and see what kind of questions you got for what I've covered so far in this little 1-hour live cast on GDI.
All right. Looks like we've got a question in already. This one comes from Bob, and it says, will the PCM FPM attempt to change the duty cycle of the check valve solenoid to compensate for a low pressure pump that has lower than spec output?
Most definitely. The question about the duty cycle to the fuel pressure control solenoid on the side of the pump, it will try to compensate if the pump mechanically is wearing, and oftentimes it is truly mechanical fit between here and the cam lobe also start to wear off, and if this thing can't pump enough, we're going to allow less of this pressure out to spill back that way, and that'll compensate, but we'll also ramp up the duty cycle higher and higher into the fuel pump in the tank with the fuel pump control module. In fact, this has been something that's been done with the pre-GDI vehicles, the SFIs and Fords and Audis and so forth for several years. They've compensated for low pressure at the rail with higher pressures, higher pump output speeds with more duty cycle in the tank.
That's great. We've got another question here. It's how bad does the deposits have to get before they will affect the computed VE of the engine?
Oh, that is a $64,000 question. And I'd like to say I could get an answer to that one and put that on the Delphi Facebook page. Now, I will try, but I've got a feeling it's one of those subjective things where it's like, okay, how bad is bad? How dark is dark, or how white is white, and so forth. I've seen cases where the valves I thought looked pretty bad and the customer had no complaint. Then I've seen valves that I didn't think looked that bad in photos other techs have showed me, and they said, oh yeah, this thing is stalling, got intermittent misfires, I cleaned the valves and it was better. So I'm going to guess the answer is going to be it will be subjective depending on the type of vehicle, the engine, and all the other variables involved. So I don't think it has to get super bad, if we could define what super bad is, in order for, in other words, you look at it and you go, gosh, I can't even tell the shape of the valve. There's that much carbon. I don't think it has to get near that point before you start seeing degradation in, of course, the volumetric efficiency test, if you're going to do that periodically throughout your customer's experience with the car, or drivability symptoms.
Great, great. We've got another question in. It says, do some manufacturers use the VVT to create a self-cleaning effect of the intake valves?
Ooh, that's a great question. And that sounds very intriguing. And you stumped me on that one. And I will have to do some research, but I know just the drivability and powertrain engineers I can ask on that one and probably get you an answer within the next week or so. Be sure to check the Delphi Facebook page. We'll have that question reposted. Very good question. And hopefully that answer in the next few days.
Yeah, remember to check back on Delphi Auto Parts Facebook for that answer. The next question we have, this one comes from Keith from Ireland, actually. It says, what procedure would be recommended for confirming actual fuel rail pressure if a sensor was to read incorrectly?
Oh my. I think I'm stumped again, because there really isn't a gauge, to my knowledge, that you could screw into that rail. I'll have to check on that one as well. In the back of my mind, I'm thinking there is a pressure transducer that will measure those higher pressures. Obviously, if you think about it, Keith from Ireland, by the way, thanks for tuning into our program, clear from over the pond there. But I'm thinking that there are brakes, for example, have PSI in the 2,000 and 3,000 range, so a gauge could be adapted. I wouldn't want to do it until I had an OE basically buy in and say it was okay for safety's sake. But pressure transducers, if you can look at the rating on them, and they would be threaded into the same spot where the pressure sensor is on the rail, conceivably could do that job. That is very provocative because, as you well know, the reason you're asking the question, sensors can become skewed. So we need to determine what's the baseline, what really is accurate. Is it really 500 or 1,000 or 2,000 PSI, or is it really something a little bit lower than that? It happens with map sensors. It happens with other pressure sensors. It could happen with this. So great question. We'll make note of it. We'll do some more research, get it out there to you.
All right, we got another one coming in. It's, can you activate the solenoid on the fuel pump to release the pressure?
Yes, you could. That makes sense. Now think about this though. When the solenoid is turned on, the pressure builds up when the pump turns. When the solenoid turns off, that's when things will be released from the system. So the normal aspect, the solenoid off, we're going to have that pressure released if the pump has made going that way. So you're just going to send it that way. I don't believe without the pump pumping you're going to be able to accomplish that. The best way is just to run it out of fuel with the relay or the fuse pulled or the pump commanded off. But you've got me thinking.
All right. Here's another question. This one comes in from Jerry. It says, is there any issue with cleaning injectors knowing now it must go through high pressure pumps?
Cleaning injectors is going to be pretty much business as usual as far as anything you would put into the fuel system to feed that high pressure system. It's going to go right in the injector. It's going to go right out. Now the jury is out on the effectiveness of that and the type of injector clogging that could occur. Obviously, there are sticky injectors, there are clogged injectors, there are drippy injectors. This does happen. As a matter of fact, one method that is being used on Fords is there is a PID for the adjusted air-fuel ratio that you can watch while you're doing a cylinder balance test. And if you don't see that move from lambda, from stoic, when you do the injector balance test, if you see it go one way, that's telling you the injector was lean, it wasn't giving fuel. You see it go the other way, that can tell you maybe you have a drippy injector. So let me do some more research on that one. We got that one recorded. I'll get you the exact details as far as injector failure patterns and more things you can do with the GDI system, with your scan tool. But other than that, as far as cleaning injectors, I am not aware of anything different as far as, you put the chemicals in the tank or you put the chemicals into the low pressure system to feed it, bypass the tank. It's going to be about the same process, but it's, you're going to have higher pressures, so who knows what's going to go on as far as the effectiveness of cleaning.
All right, so that's all the questions we have. Thanks, Dave, for answering those and taking the time. And thank you for joining us for this first Delphi training for this first webinar in this Delphi training series. Remember to like Delphi Auto Parts on Facebook for details and registration links for upcoming webinars. Thank you.